In this video, I'm going to show how to label your NMR spectra, and to do so, I'm going to be using one of the NMRs from the Fisher Esterification Lab as indicated in the top right-hand corner. That means that this spectrum is for one of the organic compounds used or produced in the Fisher Esterification Lab, so one of these three compounds, because water would be an inorganic byproduct of the reaction. And then on each spectrum, the top half is the proton NMR for the compound, and the bottom half is the carbon NMR for that same compound. Now, your first job will be to figure out which compound this NMR goes to. To do that, I'm going to focus on the H NMR and look at the zoom in section so I can see the splitting a little bit better. We can see here that there are 5 unique peaks, meaning that it would have to be for one of these two compounds because acetic acid doesn't have enough unique hydrogens to produce that many peaks. And the only real difference that we're going to see on these two compounds are on these protons here, one being an alcohol group and one being a methyl group. Each would produce a singlet, as shown here, but we can distinguish the two by looking at the integration. For example, this proton would produce a singlet with an integration of 1, whereas these protons would produce a singlet with an integration of 3. So if we look at that singlet and consider its integration, we can see that the integration is larger than that of the peaks around it. So this has to be the one with the integration of 3, meaning that this NMR goes to the product, the isopentyl acetate. Now from here, before analyzing any of the peaks, the first thing you should do is label all of the unique hydrogens on the molecule. And to be consistent, let's have everyone label the hydrogens with letters. To do this, I generally start on one side of the molecule, usually the side with the highest priority functional group, and then move across the molecule labeling all of the hydrogens. So in this case, I'm going to start with the methyl group on the side of the ester. These 3 hydrogens are all equivalent, so we can go ahead and label all of them with the letter A. And when doing this, you don't have to draw out every single hydrogen and label them all individually. Since these 3 are equivalent, you can simply label the carbon that they are attached to with the desired letter. Now we can just move down the molecule and label the rest of the hydrogens. These 2 here would be equivalent, so we can label both of those as B. And these 2 are equivalent as well, so we can label those as C. We can label this hydrogen as D. And the 6 hydrogens on the ends of the iso group are all equivalent, so we can label those as E. And since we know that they're equivalent, we only had to label one of them. Once you have all of your hydrogens labeled though, you can then start analyzing the peaks, and we already know that this large singlet is being produced by the hydrogens on the methyl group attached to the ester, so we can go ahead and label that as A. Go ahead and label your NMRs in the same way. You don't have to draw any arrows or draw out any functional groups by the peaks. You can just label the peaks with the corresponding letters. And you also don't have to label both of these peaks with the letter A since they are identical. I just wanted to show that they are the same and that one is simply zoomed in. Now we can start analyzing the rest of the peaks. For example, this one shows up around 4 ppms, being in the range for this kind of proton, which usually ends up between 3 and 5 ppms. So that would be for hydrogen B. Plus, hydrogen B has 2 neighboring protons, which is why its signal shows up as a triplet. And if we look at its integration, it's slightly smaller than the integration for hydrogen A, but not quite half as small, indicating that it would be an integration of 2, all confirming that this is the signal being produced by hydrogen B. The next most obvious peak is probably this one. It's a clear doublet with a very large integration, looking to be about twice the size of the integration for hydrogen A, so around 6. And there's only one hydrogen that would produce a signal like that, and that would be hydrogen E. This signal, around 1.5 ppms, is a quadruplet, which means it's probably for hydrogen C because it has 3 neighboring protons. Plus, its integration looks to be about the same size as that for hydrogen B, which means it would be an integration of 2, which helps confirm that this is the signal being produced by hydrogen C. Now, there's only one signal left, which means it has to be for hydrogen D, and that makes sense because even though it's hard to see how many peaks there are in that signal, because some of the peaks at the ends get really small, hydrogen D is the only one that would have enough neighboring protons to create a multiplet like that. And if you look at the integration, it looks to be about half the size as the integration for hydrogen C, so it would be an integration of 1, helping confirm that this is the signal being produced by hydrogen D. You'll notice that there are two other small peaks around 0 and 7.3 ppms. These are not signals being produced by the product, but from other compounds that are used to run the NMR. The signal at 0 ppms is being produced by tetramethylsilane, or TMS, and the one at 7.3 is being produced by the solvent used, in this case chloroform, or CHCl3. You'll want to have these labeled on all of your future NMRs as well. Now that we have all of the peaks labeled on the H NMR, we can move on to the carbon NMR, and the process is going to be basically the same. You want to draw out the molecule and label all of the unique carbons. And to easily distinguish the carbons from the hydrogens, let's go ahead and have everyone label their carbons as numbers. Then, starting at the same end as before, moving to the right, I'll label all of the unique carbons, and as you can see, there are 6 unique carbons on this molecule. Looking at the peaks now, you'll actually count 7 peaks, which doesn't match up with these 6 unique carbons, but this small grouping of 3 peaks around 77 ppms is actually being produced by the solvent, which would be deuterated chloroform, or CDCl3. And now there are 6 remaining peaks, which matches up with these 6 unique carbons. To analyze those peaks, you won't be able to use splitting like we did with the proton NMR, but you can look at the chemical shifts. For example, this peak around 170 ppms would be for the most deshielded carbon, which would be the carbonyl carbon, so carbon number 2. Now, for the rest of the peaks, you could probably do something similar and analyze them based off of their chemical shift, but there is some ambiguity and some magnetic properties that affect the carbons that you might not recognize, so you are given this 2D NMR, which I'm going to show you how to use. Basically, it combines the carbon and proton NMRs, and it shows the coupling between the protons and the carbons that they are bonded to. So on the x-axis, you can see the remaining peaks of the carbon NMR, and on the y-axis, you can see the H NMR, which we've already labeled, so I'm going to go ahead and include the letters for those. Now, each of these dots shows the coupling that exists between the protons and the carbons that they are directly bonded to. For example, if we look at the signal being produced by hydrogen B and draw a straight line out to the dot that is directly to the right of it, and then draw a straight line down, we can see a signal there, and that signal is being produced by the carbon that hydrogen B is directly bonded to. So in this case, that would be carbon 3. Then, simply moving up, you can look at the signal being produced by hydrogen A and draw a line out to the dot that's directly to the right, and then draw a line down. That signal would be produced by the carbon that's directly bonded to hydrogen A, so that would be carbon 1. From here, you can analyze the rest of the peaks in the exact same way, using those dots given to you on the 2D NMR, and that way you can label all of the carbon peaks without any ambiguity or any guesswork. Once you're done, this is what each NMR sheet should look like. You should have the molecules drawn out and all of the hydrogens and their corresponding peaks labeled with letters, and all of the carbons and their corresponding peaks labeled with numbers. And you'll also want to have all of the correct solvents labeled on there as well. You'll do this with all of the NMRs pertaining to each lab and turn them in with their respective lab write-ups.